Hey everybody, so we're back again to start part 2 of the Bayesian Nonparametric series of tutorials, 2 out of 3. And so I just want to remind you that last time what we did was we saw that there was this nice way to take this infinite dimensional model that had all these nice properties and actually come up with a finite representation of what we needed for it for our data. And so today we're going to take that a step farther and hopefully get to the point where we can use those same ideas to do inference in a way that we don't have to, actually simulate anything infinite dimensional. So let me just review last time a little bit, since you've probably seen a lot of lectures since then, despite it only being yesterday. So last time, in particular, the main thing that we did was we defined Dirichlet process stick breaking, which we also called this Griffiths-Engen-McCloskey distribution, or GEM distribution. And it had one parameter, and that was alpha. So alpha here is just some positive parameter, any strictly positive number, real number. And the output of a draw from a GEM distribution was this infinite sequence of probabilities. So row 1, row 2, row 3, et cetera. This is a countable infinity of probabilities. They're all between 0 and 1, and they add up to 1. And in particular, the way that we define this distribution, the way that we constructed it, which isn't the only way, but is certainly a particularly convenient one for simulations, as we saw, is that we just kept breaking off bits of the unit interval. So this gray thing here, again, was the unit interval from 0 to 1. And we said, OK, so each iteration, to get each one of these probabilities, we're going to draw a beta random variable, an IID, an independent and identically distributed beta random variable. We're going to throw that beta random variable away. We're going to break it off and throw it away. We're going to take what's left, and then we're just going to recursively do the same thing. We'll take a beta random variable fraction of that. We'll throw it away. We'll take what's left. We'll take a beta random variable fraction of that, throw it away, et cetera. And so we end up with the rows, these probabilities row. In particular, at the end of the day, you get all these probabilities, and you can think of the result as a probability distribution over the positive integers, 1, 2, 3, 4, et cetera. And we use this as part of a DP mixture model. So we said that these were the probabilities of data points belonging to each of the mixture components. And then finally, we could generate our data points in a mixture component as something like Gaussian around some cluster mean. OK, so let me just clarify what we did and what we did not do. So the first thing that we did was we defined this GEM. It was this distribution that had an infinite number of parts, an infinite number of probabilities. They all summed to 1, and they were all non-zero. Also, of course, less than 1. And let's compare that to this finite small k mixture model. So what is different between the GEM and if I had some prior where I put a prior on the number of clusters, and then I drew a Dirichlet distribution with that many clusters? This is a real question that I am asking you right now. Yeah. Yeah, sorry, maybe could you just elaborate on that a little bit more?
Well, for conditional on any number k that we've drawn, the prior probability of landing in any specific cluster is, on expectation, the same for each of the clusters.
So that's not necessarily true. I could choose a Dirichlet distribution with parameters 1, 2, 3, and 4, and so maybe they don't all have the same probability. Anyone else?
You have components available for new stories?
Yes, exactly. So this is the main thing. So if I have a prior over the number of clusters, and then I have this finite small k mixture model, after I draw k, I'm always going to have the same number of clusters. This is always going to be true. Whereas with the GEM, I'm always getting new clusters. The number of clusters is always growing. Again, this is the difference between components and clusters. There's always a finite number of components in the second model, and so I'm only ever going to be able to get a finite number of clusters. In the GEM model, there's an infinite number of components. I'm always getting new clusters. So it's this growing number of parameters idea. OK, what's the difference between the finite large K mixture model and the GEM? I'll answer this one for you. The difference was that we eventually sort of bottom out with this one. So we can still get a growing number of clusters. I mean, we get it for a while. We're adding in data points. We're picking up new components of this distribution. But eventually, if we're in some streaming data world or we're just getting more and more data, we're eventually going to hit a total of K clusters. Or alternatively, we might say, oh gosh, well, we don't know when that's going to happen, and so it seems like we have to know k in advance, and we don't like that, and so we maybe would like to use the GEM because now we don't limit ourselves to a particular k. Okay, finally, the rhetoric that I've been using in this is this idea of, oh, well, what we really want is a growing number of clusters, because I'm going out into the world and I'm sampling species and I expect to find more and more over time. Or I'm going out into the world and I'm reading Wikipedia and I expect to see more and more topics over time. Well, there's another model that could give me more and more latent variables over time, more and more latent groups over time, and that's a time series. Maybe right now I'm reading my chemistry book, and I see a bunch of topics in it, and I learn all of those topics. And then tomorrow I'm reading my sociology book, and that's going to be a whole bunch of new topics. And then I could read another book in a totally different area, and that'll give me a whole bunch of new topics, and that'll be a time series. And so I want to also contrast the GEM with the time series in that the GEM is stationary across the data that's drawn from it. You're not going to get new topics because new topics have suddenly come into existence. They were always there, you just didn't choose them. With the time series, you're getting new topics because suddenly new topics exist. You can combine these ideas. You can have a time series where there's a GEM over time, and so this has been done. There are ideas like, for instance, you could model Nature, the journal Nature, the science journal Nature, and you could say, hey, actually, over time, the topics that have been interesting to scientists have changed. There were topics in the 1900s that we definitely don't see anymore today, and there was this sort of slow change over time in what topics people are actually, talking about in science journals. And so there you might do something like some combination of time series and a GEM, but if you're using a GEM and all of your data is coming from a GEM, it's coming from a stationary, fixed, across the data set of probabilities. Any questions about the difference between these? Yes?
Does it have any implications in terms of the interpretation of your model? Typically when you have k-fixed clusters, you have a good interpretation.
Yeah, right.
The data came from this big component.
Right, okay, so is there an interpretation? In particular, if you have k-fixed clusters, there's an interpretation there. And so that's one in particular point to see, which is, let's say that you want to estimate the number of species in the world, or the number of topics that are out there. You don't want to use a model with an infinite number of species or an infinite number of topics for that, because there's an infinite number. So if you actually want to estimate that number, you have to use something with maybe a prior on k, or something else that you can then get evidence about. So here we're assuming that they can always grow. That's a useful approximation in a lot of cases, in particular because we don't think we're going to hit that edge, but it's not going to work for an actual infinite amount of data because everything is fundamentally finite. Okay, great. So this is what we did last time. We understood this idea of having an infinite latent number of parameters, but somehow how that let us have a growing number of parameters visible in our data. So we could have an infinite number of possible topics, but as we read more and more Wikipedia, we're discovering new topics, and that's actually a finite number of topics. We can have an infinite number of species in the world, but as we go out with our butterfly net into the wild, we're only going to get a finite number of butterflies. We saw that we get this finite representation, so even though we had this infinite model, this Dirichlet process mixture model last time, we were actually able to draw exactly from it using the fact that each data point only belongs to one group, and we only have to represent the groups that actual data points belong to. And I just want to highlight, many of you may have already seen that the last slides and the demos for last time are up on the MLSS website. You can also find them at my website, but all of that stuff is up online, and you can be playing with it. Okay, so this time we're going to use these ideas, similar ideas, to avoid the infinity of parameters for inference. Because again, when we're doing inference, we don't want to actually have to represent some countable infinite vector. We can't. We have to do something. And in fact, we can do similar things to what we did in the simulation case. Now, it turns out you can do this for the Dirichlet process. It's a little bit involved, and I'll give you a pointer to that. But what I'm going to focus on today is building up to the Chinese restaurant process. And the key idea today is going to be saying, okay, remember the DPMMM. DPMM. Two M's. So remember when we were generating from it, we generated this GEM distribution which had a countable infinity of probabilities, and then we made a draw from those probabilities, and then we made normal draws around each cluster. what's the infinite part here? The infinite part here is the probabilities. The number of draws in each cluster, that's finite. That's something we can absolutely represent, which draws go together in a cluster. The actual location of data points, well, we only have finitely many data points. That's something we can represent finitely. And so the real problem is this infinite set of probabilities. And so if we could get rid of that somehow, that would make our lives a lot easier, and it might lead to a really nice inference algorithm where we don't have to be representing some countable infinity. And so that's really going to be the tack that we're taking today. And to illustrate a little bit more concretely what I mean by this idea, let's look at it in the finite case. So we're going to start by integrating out probabilities in the finite case in order to build up to integrating them out in the infinite case. Okay, so remember this model that we had that we started off with the two-component mixture model from last time. So in the two-component mixture model, we started off by saying our probabilities rho 1, or our rho 1 is beta distributed, and so rho 2 is 1 minus rho 1. So this gives us a distribution over 1 and 2. And then we drew our cluster assignments from the categorical distribution. That is, there are 1 with probability rho 1 and 2 with probability rho 2. And what I want to do is to integrate out these frequencies, again, anticipating that I'm going to want to integrate them out in the infinite case. What do I mean by integrate out the frequencies? Well, I'd like to be able to say what the probability of a new point is, given all the previous points, the z points, the draws, without having to do anything with those beta random variables, without having to touch them, without having to calculate anything, just completely ignoring them. And this is essentially the usual thing that you do in Bayesian parametrics. It's sort of the magic of conjugacy that we can integrate this out and we're going to get a nice formula in the end. So let's do a little math this time and actually work through this problem. It's a good skill to have sort of under your hat. Okay, so the first thing that we're going to do is we're going to use the law of total probability and say that the probability of Zn equals 1, given all the other Zn's, is equal to the integral over the probability of Zn equals 1 and rho 1, given all the Zn's. Now we can split that up into two terms. The probability of Zn equals 1 given rho 1, so the probability of the next term given this underlying probability, and the posterior of rho 1 given everything we've seen before. Sort of standard Bayesian calculation. Okay, now let's evaluate each of these terms. The probability that Zn equals 1 given rho 1, well, that's just rho 1, because we're choosing each of the Zn's independently and identically from the rho 1, rho 2 distribution. So that's all I've done here in this first term. I put down rho 1. Now in the second term, I'm saying the posterior of rho 1, given the Zn's we've seen so far. What is that? Well, this is something we discussed in the beginning when we were talking about beta distributions yesterday. The beta is a conjugate prior for the categorical. And so that means that the posterior, given a bunch of categorical variables, is also going to be beta distributed. And in fact, we can calculate what those parameters are going to be. We discussed this yesterday, but you can sort of reassure yourself that this is true. What do we have here? We have A1, which was the original prior hyperparameter for the beta, plus the sum over indicators of whether we chose a 1. So this is essentially how many times did we choose a 1. Let's count up the number of times we chose a 1. And then the second parameter is A2, the original hyperparameter that we started off for the beta, plus the number of times that we chose 2. So you can see again that A1 and A2 sort of function like prior counts in the prior. They just add to the counts of 1s or the counts of 2s that we actually see in the data. Okay, so this is just a standard posterior calculation. And finally, we want to actually find out what this integral is. Well, let's plug in the form of the beta. All I'm doing here is saying bringing rho 1 down and plugging in the form of the beta distribution, which we know from yesterday. And now here's the classic trick is to note that this has the kernel of a beta distribution again. It's rho 1 to some power times 1 minus rho 1 to some other power. So in particular, what we can do is we can take this normalizing constant out, because it doesn't depend on rho 1, which is the thing that we're integrating over. So we take this normalizing constant out. Then what's left is an unnormalized beta. So we put in the reciprocal of its normalizing constant. Okay, so finally we're left with these two normalizing constants, and the key point here is to remember that the gamma function is very much like a factorial. So we can actually solve this. We can say, hey, this is like a1, a2 factorial, and this is like a1, a2 minus 1 factorial. So when we divide this by this, we're going to get a1 plus a2. This is like a2n, and this is like a2n. It doesn't really matter what they're like. They cancel. They're the exact same thing. And then finally, we have a1n and gamma a1n plus 1. So that's like a1n factorial divided by a1n minus 1 factorial. And so that's a1n. OK, so let's summarize what we did here. We said that, OK, we actually can give a very explicit, very nice, very neat formula for the probability of the next data point given the previous data points. Probability that zn equals 1, which basically describes the whole distribution of zn because it's either 1 or it's 2, given all of the data points we've seen so far, all of the categorical draws we've seen so far. And it's this a1n quantity divided by a1n plus a2n. Now you'll notice about this quantity something special. So let's pretend for the moment that we take a1 and a2, our original hyperparameters, to 0. This is exactly the fraction of data points so far that is 1. So the prediction for the next data point is the fraction of 1s we've seen so far. And the prediction for the next data point being 2, the probability of it being 2 is the fraction of 2s we've seen so far. And those prior hyperparameters, a1 and a2, just modulate that a little bit. OK, so there's actually a very special name for this process that we've discovered, this process of starting from z1 and building up to zn, conditioning on all of the z's that we've seen so far, and it's called a Polylearn. This is a very important process in probability theory. Probabilists love urns. They are so excited about urns. So this is my rendition of an urn. It's like an old Greek vase type thing, and we're going to put balls in it because probabilists love putting balls in urns. So these are the balls that we have put in this urn. This is meant to be orange. Hopefully it kind of appears orange to you. This is blue, or sorry, this is green. Yeah. OK, so we have this green ball. Discovering new colors today. We have this green ball and we have these orange balls. And the way that the Polylearn works is we start off with some number of two types of balls. So in particular, we could pretend that this was ball color 1 and ball color 2. Let's call them ball color orange and ball color green. And now we're just going to follow the rule that we just set out, the rule that we just derived for integrating out the beta from this beta categorical model. So we're going to say that we choose any ball with equal probability. So in this case, we have 4 balls. We could choose any one of them, equally probable. And we replace that ball, and we add a ball of the same color. So make sure you see that this is the same as the thing that we did up here. So we start off with A orange balls that are orange and A green balls that are green. We pick one out, and the probability of picking out an orange ball is the number of orange balls divided by the total number of balls. That's A1n divided by A1n plus A2n. And if we get it, we put one back. So that's the probability of getting an orange up here. OK, so can anybody tell me if I do this? So let's say that I start off with A orange balls and A green balls, and I repeat this. Every time I get an orange ball, so I randomly choose one of my balls. Every time I get an orange ball, I put an orange ball back in. I put the original one back in, and I put an orange ball back in. Every time I get a green ball, I put the original green ball back in and a new green ball back in. What's the limiting proportion of orange balls relative to the total? Hint, it's random. What distribution does it have?
Beta A1, A2?
What was that?
Beta A1, A2?
Yes, absolutely. It's beta A1, A2. Does everybody see why that is? Let me go over it again. So what we did was we started off with this general model where we said rho 1 is beta distributed. And then what we could have done is we could have drawn Z1, Z2, Z3, Z4, everything, independent and identically conditional on rho 1 and rho 2. And I'm telling you that we just derived that the same distribution of Z1, Z2, Z3, Z4, etc. comes from this Polylearn distribution. And so if it has the same distribution, well, we know that if we started off with this beta distribution, this beta distributed row 1, and drew all these Z1s, and then we looked at the limiting proportion of Z1s, it would have to be row 1, right? Maybe that's not so controversial. Hopefully that's not so controversial. So again, if I start off with this original generative model, I generate a random row 1 and row 2, and then I draw an infinite number of Zns to be either 1 or 2 based on probability row 1 for 1, and probability row 2 for 2, then the limiting proportion of things that are 1 is row 1, and the limiting proportion of things that are row 2 is row 2. And so now we're just doing the exact same thing. I've described an equivalent model for the Z's, and so their limiting proportion has to be row orange, and the limiting proportion of green has to be row green. I'd love to take some questions to clarify this. Or is it all super clear and you're just wondering what to do? Yes?
I don't find it obvious that it converges. Like the expected value is I find convincing. But why doesn't it diverge?
Right, okay, so the key point here is that you shouldn't have to calculate anything here. You should really just have to think about the original model. So think about the original model. So suppose I draw my beta distributed row 1 and row 2. And then I make these IID draws conditional on row 1 and row 2, where every one of them is 1 with row 1 and probably 2 with row 2. Now, it's exactly equivalent. I'll have the exact same distribution on Z1, Z2, Z3, etc. as this Z1, Z2, Z3 if I do a Polylearn. If you don't believe that we proved that, just assume it for the moment. Then over here, the limiting distribution of Z1, of the sum of the Zn's, the average number of Zn's being equal to 1, is definitely row 1, which is a beta distributed random variable, right? I mean, here that was just the generative model. And so over here, if it has the same distribution, we don't have to do any calculations. It should be true, right? Yes?
So the question is about what are the parameters A1 and A2?
Great. The parameters A1 and A2 are anything that is a positive number that is strictly greater than 0. You'll notice that right now I have drawn an integer number of balls, so let's just pretend that they are actually positive integers for the moment, but this is much more general than that. That is sort of purely for the purposes of my cartoon.
Yeah, but my question was more like, does it depend on the initial condition, and how does it depend on the initial condition of the...
You mean how do we get A1 and A2 if we start down here from the limit? Is that the question?
Yeah. Yes.
Yes. Okay, yes. So we can recover them from the limit.
Yes.
I kind of don't want to necessarily get into exactly the formula that you would use, but you absolutely can. Well, I mean, I guess basically, actually, there's nothing to it. It's just the number of balls of each color. So A1 is the number of, or A green is the number of green balls, and A orange is the number of orange balls. So it's however you start. Yes?
Just to clarify, you're not saying that we end up with the same fraction of red to green balls in the urn, but that it's distributed according to the beta of the pieces?
Yes, yes, this is exactly right. We're not ending up with some fixed fraction, especially not some fixed fraction that's equal to the original fraction. We're going to end up with a random variable. And that random variable is going to have some distribution, and that distribution is going to be beta A1, A2, where those are the beginning number of balls. Yeah. Yeah.
I don't understand why it doesn't happen. I mean, in this case, for example, I think the effect of the get-reacher would happen
Yeah.
Because, and then I think that in the limit, so the limit is a number that will never be reached, but it's like an upper bound. I think the limit should be 1.
Yeah, that's fascinating, but it's not true. And the reason is because of this proof. So you can do this. You can actually do this for yourself. So you can run this Polylearn. You can find that you're just running this exact thing that we just described, that probability that Zn equals orange is equal to the proportion of orange that we see so far. And it will be amazing. You will actually find that the limiting distribution is beta distributed. And the reason why is really that it is exactly the same distribution, the marginal of the z's in this joint probability distribution with the rhos and the z's is exactly the one we just derived. It's the exact same distribution as if we had done the beta draw and then the z draw. And so it must be the case that we have this underlying beta proportion.
So sorry, so you mean that the limit is the mean?
What I mean for the limit is what is the limiting distribution of the percentage of orange divided by the total. So for any particular Polylearn, I can take this limit and I'm going to get some number. And I'm going to tell you that it's not going to be, well, first of all, it obviously has to be a number between 0 and 1. And so I take this limit and get some number, and I'm telling you that that number in the end is beta distributed. So it's like making a draw from a beta A1, A2. And again, the reason is I could make this row 1 an infinite series of z draw, and it has the same, the z's there will have the same distribution as if I made all these z's draws. And so it must be that the limiting distribution, we know the limiting distribution over here, the limiting proportion of oranges is row 1 distributed, so the limiting proportion of oranges over here has a beta distribution. I often find actually simulating these things to be the most convincing thing to do, so I recommend trying it out. Okay, this is pretty important though. I mean, basically the idea, everything that we're doing is going to be integrating out this beta, so I'd be happy to take more questions to make sure we understand this, but otherwise I'll head on. Yeah?
Sorry, just to complete exactly, we're doing the Polylearn to generate beta distributed around variables?
Yeah, so the reason that we're doing the Polylearn is this idea that what we'd like to do ultimately with the Dirichlet process is we had this sequence of probabilities that was GEM distributed. And then the way that we drew the cluster assignments was we drew from that distribution. So we said, okay, we have cluster 1 with probability row 1, cluster 2 with probability row 2, et cetera. And so the problem was the infinite thing was this distribution, this underlying distribution, the row 1, row 2, up to infinity. And the finite thing was when I actually make these draws, 1, 2, et cetera, and so on. So if I know just the z's, just the assignments of data points to clusters, I can represent that on a computer. I can't represent this infinity of cluster probabilities. So what we want to do is go back to the finite case and say, okay, what happens there? Can I get rid of the cluster probabilities there? And so the whole point of this is to try to get rid of the cluster probabilities, which in this case are beta distributed. So here we have a generative model. We generate row 1 and row 2, they're beta distributed, and then we make a bunch of draws, 1 with probability row 1 and 2 with probability row 2, and we just keep doing that. And what we'd like to do is we'd like to say, what's the distribution of the z's without involving the rows, just on their own? And so that's what we did here. We calculated probability of Zn equals 1 given all of the other z's. And so what I wanted to say is that this contains all of the information that we need. The fraction of z's that are equal to 1 in the end of the day are going to be row 1. The fraction of z's that are equal to 2 at the end of the day are going to be row 2 because we're drawing them from this discrete distribution that has row 1 with probability row 1 and row 2 with probability row 2. And so that's the idea of the Polylearn. We just make these draws. And so the fraction at the end of the day should again just be row orange, which has a beta distribution. Okay, So this is the kind of thing that maybe I'm going to leave you to do some exercises on your own, wrap your head around, run some simulations. It's kind of crazy stuff when you first see it. It definitely seems like you're making all of these. I mean, there's another infinity coming up here. You're making these infinite draws from two probabilities. So it's reasonable to think that it might be doing something weird. And it's kind of amazing that it doesn't. Yeah.
But I mean, the ZNs are always going to be finite, right?
Yeah, well, ZNs are always going to be 1 or 2.
Yeah, no, but I meant the number that we
Oh yeah, the number in real life is always going to be finite. This is totally just a thought experiment. Yeah, absolutely.
So the ones to find that number, the ones that we have, are not going to be. If you take the
Yeah, so if you take the fraction for any fixed n, this won't be beta distributed, but it might be close. Okay, so let's take this idea a little bit further, and let me just clarify one last thing here. So I said you choose any ball with equal probability. That kind of relies on having a finite number of balls, and in particular, an integer number of balls. But I said that A1 and A2 could be any positive number. So in fact, I can actually have fractional balls, and then I choose them with probability proportional to their mass. It's the same thing that we just did. In fact, it reduces to the previous case when I have an integer number of balls, but this is just slightly more general for when the A's, these hyperparameters, don't have to be exactly integers. Yeah?
And then we can't add that mass back in.
No, so yeah, great question. So you choose any ball with probability proportional to its mass, you replace that weird fractional ball, and you add one whole extra ball. You always add one extra ball of the existing color. Yeah. Okay. So what if we do this in the multidimensional case? So now I have a bunch of frequencies that are Dirichlet distributed. So I have row 1, row 2 through row k. They're numbers between 0 and 1. They add up to 1. And the idea is that I'm going to make categorical draws. I'm going to say that I draw from this distribution, row 1, row 2, row 3, etc. Draw row 1 with probably row 1, 1 with probably row 1, 2 with probably row 2, etc. Now, we can calculate, and I'll leave this to you. It's very similar to the beta Bernoulli calculation that we did before. And it's going to be that Zn equals k. The probability of that, given the Zns we've seen before, is again essentially the fraction of k's that we've seen so far. And when I say essentially, what I mean is that akn is the original hyperparameter ak plus the number of k's that we've seen. So if we sum up the indicators of each Zn being equal to k, that's equal to the number of k's we've seen so far that are z's. And so again, we get this sort of thing that looks like a fraction of k's we've seen, but is a little bit different because we started off with these hyperparameters. And the result is this is a multivariate Polylearn. So we start off with our urn, which is a very nice urn, and it has 4 colors in it now. So 4 colors, various balls. They might be fractional balls. It doesn't matter. And what I'm going to do is I'm going to do the same thing. I'm going to choose any ball with probability proportional to its mass. And then I'm going to replace that ball, whatever it was. If it was 1/5 of a ball, I put that 1/5 of a ball back in. And as was pointed out over here, I also put in a full ball of the same color, no matter how small that fractional ball was. And now, can anybody tell me what the limiting distribution of the number of orange, the number of green, the number of red, and the number of yellow divided by the total as a vector is? I hear some correct rumblings.
I see no reason why this should change from the class exercise. I mean,
Yeah, that's a great idea. Keep going with it. Name an exact distribution.
so what's going to happen is you have the exact Dirichlet one. It's
Yes.
compared to the first.
Yes, you are absolutely right. That is exactly what I was looking for. So you're going to have a Dirichlet distributed proportion with A orange, A green, A red, and A yellow, the hyperparameters you started with. That's perfect. Are there any questions about this? Okay, so the whole, oh, great. Yeah.
Probably should have asked that already.
No problem.
So maybe we could go back to that because that's the
To the beta slide?
yeah.
Sure.
So we said that in the end we'll end up with the same distribution, still comes from the same beta distribution as the first one.
Yeah.
But actually, in the process, we always update our sort of beta parameters
Mm-hmm.
to posterior. So why don't they come from the posterior?
So in what process do we update beta parameters to the posterior? Because the number we start off with has no beta distribution. The number we start off with is just A1 and A2. So there's no beta that pops up anywhere here. And every step we make doesn't involve a beta. It's just this Polylearn step where we take a ball and put one back in.
Yeah, but that's the same as updating the posterior of the beta distribution.
It's actually not. It's the same as drawing a new value from the beta distribution. So Zn1 is the same distribution as if I had just drawn another IID value from my beta. So I'm actually not calculating a posterior anywhere here. I'm just making a bunch of infinite IID draws conditional on the beta. And then I'm saying, okay, well, let's say that we've seen everything before. Then what's that distribution? There's like a posterior that's implicit in the calculation of it. But in terms of actually getting the z's, these z's are like IID draws from this beta. Okay. Okay, so at this point, well, we'd like to have such an urn for an infinite process. It would be nice to be able to say, hey, you know, this was a nice finite thing. We never had to deal with this underlying Dirichlet distribution. We just were able to look at these nice finite steps where you say, okay, I have this number of balls. I make a decision based on the balls that I've seen, and everything's nice and finite. The problem with immediately going to a Dirichlet process with this, or a GEM, is that, well, I can't start off with an infinite number of balls. I can't start off with, you know, 0.5 yellow and 0.5 green and 0.5 orange and then name me an infinite number of colors and I start off with all of those. That would defeat the whole purpose. I don't want an infinite number of parameters. And so I'm going to introduce a new urn with a very special magical 8-ball that isn't part of it, which we'll call the Hoppy urn or the Blackwell-McQueen urn. Okay, so it starts off with this special weirdly shaped magical 8-ball. And the magical 8-ball behaves in a way that no other ball behaves. So when we choose our ball, we'll choose any ball with probability proportional to its mass. So in particular, we'll choose the magical 8-ball for sure on the first round because it's the only thing in the urn. If we choose the special black magical 8-ball, then we replace it, but we don't add another magical 8-ball. We add another ball of a different color, a color that we've never seen before. And if we choose a boring, regular colored ball, then we replace it and add a ball of the same color. So this is the same thing that we did before for the Polylearn. Okay, so let's go through an example of this. So let's say that I start off with my urn and my special magical 8-ball. Well, on the first step, I have to draw a ball of a new color because the only thing that I could have drawn was the magical 8-ball. And so I have to take it out, put it back, and put it back in with a ball of a new color. Okay, so on step 2, I could have either drawn the magical 8-ball or I could have drawn the orange ball. In this case, I happen to draw the orange ball, and so I put it back and replace it with another orange ball. In step 3, I could have drawn the magical 8-ball or I could have drawn the orange balls. And in this case, I happen to have drawn the magical 8-ball, and so I put in a ball of a new color and it's green. I do the same thing, step 4, it turns out I drew the magical 8 ball, and so I get another ball of a new color. Yeah?
Does the black hole has exactly the same mass as the other one?
Great question. The black one we will assume in general has mass alpha. So it'll be some mass, you get to choose it, but it doesn't have to be 1. All of the other balls have mass 1. Okay, great. Oop. I sort of just showed you the answer, but let me ask you a question. What is the distribution, starting from step 1, of the number of orange balls and the number of not orange balls? And I'd also like you to maybe talk a little bit about it, because I might have just flashed it. So here are some distributions that you know so far. Beta distribution, Dirichlet distribution, GEM distribution, Polylearn. What is the distribution of the number of orange balls and the number of black balls, sorry, the number of orange balls and the number of not orange balls, any ball that is not orange, including the black ball and including other colored balls, starting from step 1? Feel free to throw some crazy answers out there. Oh, is there a?
Beta?
It is not beta. Polylearn is a great guess, because we are definitely dealing with an urn. Can somebody tell me the parameters of that polylearn?
1 and alpha?
Right, so why would you say that the parameters are 1 and alpha, and which one does 1 correspond to and which one does alpha correspond to?
Well, we know that after the first step we have 1 orange ball and alpha other balls.
Mm-hmm.
The magic ball, which we cannot distinguish from the other balls, they're just non-orange.
Yeah.
So step 1 is the start of a polygon.
Great, exactly right. Okay, so let me just repeat that. So at step 1, we have 1 orange ball, and we have alpha not orange balls. Now going forward from step 1, whenever we choose an orange ball, we'll put another orange ball into the urn. And whenever we choose a not orange ball, we'll put a not orange ball into the urn. That's a polyurn. It's a polyurn that starts off with parameter 1 for orange and parameter alpha for not orange. So starting from step 1, the distribution of orange and not orange is polyurn 1 alpha. Okay, let's look at step 3. At step 3, we introduce this new color green. Now let's suppose that we look at the urn, but we don't look at the orange balls. We look at everything but the orange balls. Starting from step 3, if we ignore the orange balls, what's the distribution of green balls and not green balls? Want to be a little bit more explicit? Yes, and what does the 1 correspond to?
1 for the green ball and alpha for the
Great, great. So exactly right, it's the same. If we ignore the orange balls, starting from step 3, we have 1 green ball and alpha not green balls. Going forward from that step, whenever we choose a green ball, we're going to get another green ball. And whenever we choose a not green ball, we're going to get a not green ball. And so this is a polyurn 1 alpha. Okay, and I think that you can anticipate where I'm going with this. If we go to step 4, where we see this new color red, we can say what's the distribution of all the colors that we haven't seen so far. Okay, so, or like get rid of the colors we've seen so far. So get rid of orange, get rid of green. What's the distribution of red and not red? It's, surprise, polyurn 1 alpha. Yeah.
Are you ignoring the previous colors just for counting or also for going forward through the steps?
For all the steps in the future, for all the steps in the past, for everywhere. So I'm just saying completely block out from your mind. So I'm saying do the actual hoppy urn. Like actually do the hoppy urn. But the thing is, going forward in the hoppy urn, only greens affect other greens. The only way you're going to get a green in the future is by drawing a green. So we could just sort of pretend that they don't exist, don't look at them.
So in other, you don't take into account orange and green.
I'm not sure if I...
When you count in the number of others.
Yeah. So this is, so the number of others, I take into account that they're not green and not orange, but I don't take into account anything else. So this is just for the purposes of counting. So I run the hoppy urn, and I just want to count the number of reds that are in it. And I want to count the number of things that are not orange, green, or red. The total mass, anyway. So that's all I'm doing. I'm not changing the urn in any way. I'm still running a hoppy urn in all possible ways. I'm just counting the number of things that are red or not orange, green, and red. Great. Any other questions? Okay, so why do we do this? That was pretty random. Here's a bunch of poly urns. Well, you'll recall from a couple of slides ago, and we spent a little time on it, so hopefully it's deeply ingrained in your mind now, that the limiting distribution, the limiting fraction of oranges under this poly urn is beta distributed with parameters 1 and alpha. So the limiting proportion of oranges is a beta distribution, has a beta distribution with parameters 1 and alpha. The limiting proportion of things that are not orange is 1 minus V1, this beta distribution. The limiting proportion of things that are not orange, but are green, is beta 1 alpha distributed. That's V2. The limiting proportion of things that are neither orange nor green is 1 minus V1 times 1 minus V2. The limiting proportion of things that are red is 1 minus V1, 1 minus V2 times V3. Does anyone find that this sequence looks familiar from anywhere? Yes, it is the GEM. I'll assume that your laughter means you were saying GEM. This, in fact, is exactly the GEM distribution. We have proven that the Hoppy urn, Blackwell, McQueen urn is the marginal distribution of the GEM. If you have a GEM distribution for your probabilities, your row 1, your row 2, your row 3, your row 4, and then you make draws from that distribution. Z is row 1 is 1 with probability row 1, it's 2 with probability row 2, etc. You can integrate out that GEM. You cannot deal with that infinite number of probabilities at all by using this urn. This gives us the marginal distribution of those cluster assignments. There's another name for this urn that you may have heard in life, in your machine learning livelihoods, and it's called the Chinese restaurant process. This is exactly the same thing we just did, but I'm going to rephrase it in terms of a culinary metaphor. Each customer walks into the restaurant, and they either sit at an existing table with probability proportional to the number of people who are there. Those are the balls in the urn. Each table is like a different color. Or they form a new table with probability proportional to alpha. Remember, we had this great question about what is the mass of the magical 8-ball in the Hoppy urn. It's alpha. Okay, so the first person walks into the restaurant. There's no table, so they form a new table. That's like the first black ball in the Hoppy urn. We have to get a new color. And now we also get some sort of dish at the table, which is usually some cluster-specific parameter. Everybody at the table will eat this delicious dish. And then the restaurant prepares a table in case new people come. Okay, the next person walks into the restaurant. They join an existing table with probability proportional to the number of people who are there. Maybe they join table 1. The next person walks into the restaurant. They join each table with probability proportional to the number of people who are there, and they join a new table with probability proportional to alpha. Maybe they form a new table, and therefore it gets a delicious dish. And again, that dish is like a cluster-specific parameter. It's like the means of our Gaussian mixture model. The next person walks into the restaurant. They happen to form a new table. It gets a dish. And then because I sort of ran out of space in these slides, it just so happens that everybody else joins an existing table. But I swear that that actually happened in probability. But again, you just do this thing again and again where each customer joins a table with probability proportional to the number of people who are there. Just like in the urn, you chose a color with probability proportional to the number of balls of that color. And the new table, which has mass alpha, probability mass alpha, is like the magic 8-ball in the hoppy urn that let you form a new color. So the naming of the Chinese restaurant process, so I believe Aldous in his exchangeability manuscript in 1983 credits this to Jim Pittman, and my understanding, and this may be apocryphal, is that basically they were observing Chinese restaurants in the San Francisco Bay Area and saying, oh gosh, I noticed that you can always fit more people at a table and they can always put in more tables in these restaurants. And so they thought they would make a process based on that. But actually, these ideas, the hoppy urn and the Blackwell-McQueen urn, if we go back, date back to even further. Oh, I should have a reference on that slide. I'll add it later. So the Blackwell-McQueen paper came out in 1973, same as the Ferguson paper on the Dirichlet process, and the hoppy urn paper, I believe, came out in 1984 or 1982. Okay, so any questions on the hoppy urn, on the Chinese restaurant process, on the Blackwell-McQueen urn, which is the same as all the things I just mentioned? Yeah.
I think I have heard of a somewhat similar process in graph theory, preferential attachment.
Yeah, it's definitely a preferential attachment scheme in that rich gets richer here. There's another process, the Pittman-Ure process, which we might have some time to talk to, where rich gets even richer. But this is a particular scheme like that, yeah. Okay, great. So the nice thing about the Chinese restaurant process and all of these urns is that this is finite now. We know that it represents a GEM distribution and a sequence of draws from that distribution. So there's something infinite going on. There's something that's going to make sure that we always are getting, as we get more and more data points, more and more new tables, which are more and more new parameters. But the representation is fully finite. There is no point at which we even consider instantiating an infinite number of random variables. So that seems like it would be really nice for inference, and in fact it is. So let's build up to that now. So along the way, we proved that this was the marginal for the categorical likelihood with a GEM prior. I hope you agree that that's true in the same way that we have this Polylearn marginal for a beta with a categorical and this multivariate Polylearn for a Dirichlet with a categorical. And I want to make one more point, which is that in all of these urns and these Chinese restaurant processes, there was nothing that we really used about order. It was never important that all these customers be seated at table 1. They're just seated at a table together. That's the whole idea of clustering, in fact, that somehow, all of these points go together and they're in a group together, and then we generate them from their cluster mean, and all of these points go together and they're in a group together and we generate them from their cluster mean. And nothing would have changed if we said that all of these points were in cluster 2 and all of these points were in cluster 1. It would be exactly the same clustering, right? So here we could say that Z1, Z2, Z7, Z8 equals 1, Z3, Z5, Z6 equals 2 based on which tables they belong to. But we could have equally said that Z1, Z2, Z7, Z8 equals 2, and that these equal 1. There's nothing special about the ordering here. And so in particular, it's often useful to use a different notation, a so-called partition notation, where to represent that 1, 2, 7, and 8, customers 1, 2, and 7, and 8 are eating at a table together, we write them as a set. And 3, 5, and 6 are eating at a table together, we write them as a set. And 4 is eating at a table by itself, we write it as a set. And then finally, the full partition of these 8 integers is a set of sets, because there's no ordering on these sets. So this gets rid of this sort of weird labeling thing that isn't important to the clustering problem. So when we do this, we call this a partition, in this case of 8, but in general it could be of any positive integers, or in fact all the countable integers. And this in fact is a set of mutually exclusive and exhaustive sets of the integers that are in these brackets. So that is the definition of a partition. And that is what we are constructing with this Chinese restaurant process. So let me do one last thing as we're running out of time. Let's find out the probability of this seeding, and then we'll finish up and get to our inference algorithm next time. Okay, so what we want to do is find out what is the probability of seating people in this order. And so let me just give you the first answer. The first person comes into the restaurant. The probability of them sitting where they do is 1, because they only have one choice. They have to form a new table. We can think of this as alpha over alpha because, again, you form a new table with probability proportional to alpha, and you join an existing table with probability proportional to the number of people who are there, but the only option was alpha, so it's alpha over alpha. What's the probability of the second person sitting where they're sitting? And this is a question for you.
Alpha divided, alpha divided by alpha.
There's definitely an alpha in there.
Yeah, so
But where?
1 divided by alpha plus 1.
Exactly. So it's 1 because they're joining a table that already has one person, the 1. And then it's 1 plus alpha because there's the table with one person and the potential new table which has probability mass alpha. Okay, what's the probability of the third person sitting where they're sitting?
Alpha over alpha plus 2.
Exactly. Alpha because it's a new table, alpha plus 2 because there's the potential for a new table and 2 people are already here. What's the probability of the fourth person sitting where they're sitting? I heard various murmurings.
Alpha over alpha plus 3.
Yes. Alpha over alpha plus 3. Alpha because it's a new table, alpha plus 3 because there are 3 people so far and there's always the potential for the new table. Okay, I'll just sort of tell you from here. Let's look at 5. Well, there was one person sitting at the table where 5 is, that's the 3, so it's going to be 1 over alpha plus the number of people so far. Next, we look at 6. There are 2 people at that table, so it's 2 over alpha plus 5. Next, we look at 7. Well, 1 and 2 are sitting at that table so far, so it's 2 over alpha plus the number of people so far before we get to 7, so it's 7 minus 1. And then finally, we go to 8. Well, there were 3 people sitting at that table already, so we put 3 in the numerator, and then we have alpha plus the number of people up to 8, that's 7 in the denominator. Okay, so let's very quickly see if we can find a general formula for the probability of a seating of this form. So in particular, let's suppose that I have n customers that have walked into my restaurant, total of capital N customers. There are k sub n tables by the end of those n customers. They've formed k sub n tables. And let's say that there are nk people at the very end at table k. What is the denominator going to look like? It's a lot of, maybe let's get a hand. I'm hearing murmurings.
Sorry, is the sum?
Do you want to go for it? Okay.
It's going to be a sum. Is alpha plus the sum of all the people in all tables?
That's close. Let's look at the denominator in the probability that we just calculated. So what form does this denominator have? It looks like alpha times alpha plus 1 times alpha plus 2 all the way up to alpha plus 7.
Gamma plus 7 over gamma plus.
Maybe, yeah, so you're, I mean, you're pretty much it. So basically, let me not write it in gamma notation just to be super clear what's going on. The proposal is we're going to start with over alpha, and we're going to take product up to alpha plus the total number of people in the restaurant minus 1. Why is that? Because each person who walks in, the first person, there's only the potential for a new table. The second person, there's the potential for a new table, and there's one person already there. And you go all the way up to the last person, where there's the potential for the new table, alpha, and there's n minus 1 people who have already sat. So this is just a product over all of the terms of alpha, alpha plus 1, alpha plus 2, all the way up to alpha plus n minus 1. Okay, for the numerator, can anybody tell me what the term is going to be that represents the new tables that were created?
Sure, alpha to the kn.
Yes. Why alpha to the kn? Because in the numerator, every time somebody chooses a new table, it's with probability proportional to alpha. So there are going to be kn total new tables. It'll be alpha to the kn. Okay, last one. Can somebody tell me the term for the existing tables, for the number of people who sit at the existing tables? Close.
So for example,
Let's see if we can get somebody new in here.
the product of the NK factorial
It's just very close. Is there something slightly different?
NK minus 1.
Yes. So you're all totally on point with the product over the tables of nk factorial, but it's nk minus 1 because it's the proportion of people who are already there. So when I'm a new person walking into the restaurant and making a decision, I say how many people are already at this table. So I say nk minus 1 divided by everything else. Okay, so I can take a few last questions, but we're basically done for the day, and then we're going to use this Chinese restaurant process immediately next time to come up with an inference algorithm. And you can start thinking about right now what we know about the Chinese restaurant process and what will be useful in particular for Gibbs sampling. Do I have time for a final, if there's a final question or two? Yeah.
I'm a bit confused. Isn't there multiple ways that the people could like first decide to attach to that table and then to that table, and they would all lead to the same distribution? Wouldn't we have to account for that?
Right. So here we're saying what is the probability of this particular permutation?
Okay, so the order is matters in this one.
The order doesn't matter in terms of coming in, but we're doing one instantiation of that, if that makes sense. Maybe we can talk a little bit after, given that we're short on time, and I can come back to it in the beginning of the next one. Anything else quickly? Okay, great. I'll leave it off to announcements.
Okay.